Welcome to my talk here on Limit Summer School. My name is Alex Huebner and I'm going to present you some ideas on how to use cross-validation in the cluster expansion method. You can see here our common problem. To calculate formation energies of alloys by first principles is computationally demanding. For many applications, quick calculations are needed. For example, to find the partition function of this thermoelectric alloy here. To quickly calculate the energy of formation, we resort to model building, and our model building technique is a cluster expansion method. In the cluster expansion, we start with a non-substituted crystal, substituting a number of atoms leading to a configuration for which we calculate the energy by first principles. Then we introduce clusters, which are subsets of lattice sites, and define correlations between the configurations and the clusters contained in the correlation matrix. Then we define a model which predicts the energy of the configuration sigma by introducing a parameter for each cluster J alpha. In order to measure the accuracy of this model, we mean the square of the error of the predictions over all the configurations that we have. Minimizing this quantity leads to optimized parameters, and with them we can rewrite the predictions of the energy using the projection operator of the model defined as such. Another important quantity is the cross-validation score, which is almost a mean square error with a single but important difference that the predicted energy is predicted without the configuration itself, so that we have to make regressions for each configuration. To illustrate the meaning of the cross-validation, you can see here a toy model's energy over the configuration, where the energies are generated by a parabola plus a small noise. And now we introduce models to it. Here, a polynomial of 0th, one of second, and one of 9th order. You can see that even though the polynomial of 9th order fits the data the best, the predictions remain questionable in a certain area. And using the cross-validation score, we can detect this. When excluding the outermost right point and building new models, you can see that the new models indicated by the dashed line, explicitly the red one, totally fails to predict this outermost right point, while the model of the parabola still is quite good. And so the cross-validation can be used to detect overfitting. And in this sense, we can find an optimal model. Here you can see another aspect of the formula to find the cross-validation score I've just shown you. To determine one addend of this sum scales very fast with the number of clusters we introduce to our model. The regressions we make are computationally slower than a formula you can see here, where we predict the energy with all the configurations and divide by 1 minus the sigma diagonal entry of the projection operator. In this work, we have generalized the formula to leave many out cross-validation, understood instabilities in the upcoming formula and devised ways to circumvent them, and found a relation from this formula to the noise in the data. So first of all, to the leave many out cross-validation. When we minimize the mean square error for all the not excluded configurations, when excluding more than one, we find parameters for this subset. And rewriting this cleverly and putting it back into the definition of the cross-validation, we find this new formula here, where n is the number of sets we've taken out, aleph of e is the size of the excluded set, and PEJ is the submatrix of the projection operator corresponding to the excluded set. So what is faster now, the old approach or this new method? When we keep everything fixed but change the number of excluded configurations, the new approach indeed scales, and it scales badly, while the old does not. But if we keep the number of excluded configurations fixed, while changing the number of clusters, we see that the new approach does not scale at all, while the old does. And in fact, in our settings, it is usually the case that the number of excluded, or the number of clusters is bigger than the number of excluded configurations. So that for us, this formula is beneficial. Another important aspect I want to stress is the instability issue. You can see here a model with just one parameter, which is, in a sense, a symbol for this. The model has just one parameter and is indicated by the black line. We have a number of points which are close to the origin with a small correlation and one with a big one. When we change the position of one of these points close to the origin by a certain amount, the model does not change much, as indicated by the blue dashed line. Well, when changing the point with the big correlation by the same amount, the model changes a lot by the red dashed line. In the ultimate limit that we push all the blue points in the origin, this causes an instability. But knowing this instability gives us easy means to circumvent it by just adding one more configuration here with the similar big correlation. This is indeed a possibility to choose configurations for the cluster expansion. And even though in cluster expansion it's a higher dimensional problem, this picture still works, because one of the diagonal entries of the projection operator simply goes to 1. The third point I want to stress is that we found a CV noise relation. We aim to limit the number of ab initio calculations for our model building, because we often encountered the situation that even though we've raised the number of ab initio calculations, our prediction became not much better, in fact. And so our idea was that when the error of the predictions which comes due to the missing clusters in our model becomes comparable to the noise in the overall data, then that should be a break-off criterion of our ab initio calculations. Using Fisher-Courant's theorem then leads to the following relation, that for the model with the lowest CV and this criterion, the average noise level has to be bigger or equal than the root mean square error that we find. And this is then a tool to, as I said, break off the number of ab initio calculations. Here you can see the numerical proof of this relation, where each point corresponds to one model with 9 parameters and numerous data points. And you can see that these quantities here that should be smaller than 1 due to the relation are indeed smaller than 1. All this can be applied to real alloys and real cluster expansion and have been to the barium aluminum silicon case of Maria with real DFT data by the full potential all electron code exciting. To conclude, we found an expression for the leave-many-out cross-validation, understood the origin of the instabilities in the formula and devised ways to circumvent them, leading to a configuration selection tool. We found a CV noise relation and a criterion to limit the computational effort with it. I want to especially thank Claudia Draxel, who gave me lots of help and advice in my work, and Santiago Rigamonti for all he taught me and for the intense cooperation. And I want to thank you for your attention.